Electrical power. In this video, we're going to have a look at what is power, and we're going to use the electron shuffle model to explain what we mean by power. So here's a simple circuit of a battery and one resistor. And we see that the current goes from the positive end of the battery, gets pushed out of the positive end of the battery, through the resistor, and back into the battery. We know that according to Coulomb's law, the current depends on the resistance and depends on the voltage. The higher the voltage, the greater the current is going to be, and the greater the resistance, the lower the current is going to be. So the movement of that current depends on how big the voltage is and how big the resistance is. So let's just revisit the electron shuffle model on how that current moves through the circuit. Now we know that voltage pushes the charge carriers through the loop. The electrons are the charge carriers. Movement of the charge per unit time, we call that current. So current is equal to charge per unit time. Now charge is measured in coulombs and time is measured in seconds. So current, we know that that's measured in amperes. So 1 ampere is equal to a coulomb per second. Now, according to Ohm's law, if the voltage is increased, current increases through the same resistor. So current is equal to voltage divided by resistance. Now also recall that as the charge carriers move through the battery resistor loop that I showed you on the previous board, they pick up energy from the battery and move into the resistor where it is converted into light, heat, motion, or something similar. Now, in electrical terminology, energy is equal to the product of the charge and times the voltage. So whatever the charge that's being carried times the voltage, that's the energy that's being transferred to the resistor. Now in general terms, be electrical or mechanical, power is energy divided by time. Now when we talk about power, we're talking about power being consumed or energy being consumed per unit time. That's what we mean by power. So let's look at creating a formula. What I just said is that power is equal to the energy, Q times V, divided by time. Now earlier we said that Q times V is equal to current. So we can replace, Q divided by T is equal to current. Current is charge per unit time. And if we multiply that by voltage, we get this formula, P is equal to IV. This is the common power formula, although if you know something about the charge involved, you can use that also. Now, V is measured in volts, I is measured in amperes, and power, you may recall from mechanics, power is joules per second, and 1 joule per second is equal to a watt. Now, if we take this formula and we combine P is equal to IV with Ohm's law, V is equal to IR, you'll get this combination formula, which relates power, current, and resistance. Here, the power formula relates current and voltage. Here, it's current and resistance. So you can use one or the other depending on your need. So power, what does that actually mean? Well, when we say power, in an electrical circuit, we're talking about how fast the energy is being consumed by the device, or how fast you're putting energy into the device, how bright a light bulb is. So the brighter it is, the faster that light bulb is consuming energy. We know that we measure the brightness of a light bulb in terms of its wattage, which is in terms of its electrical consumption. A 100 watt light bulb consumes more energy than a 60 watt light bulb. And therefore, a 100 watt light bulb will produce more light. What else does it mean? It means how fast a motor turns or how fast work is being done. Remember, work is equivalent to energy.